Okay, this is our video about gears, pulley drives, and sprockets. And this is going to go with several more activities you're going to do with calculations. And I've given you a handout. What you should do with that handout is cut the pieces and just glue them in as we get to them on the video. As you get to the right part on the video, find the right handout, glue that in, and then take the notes there. I basically just gave you the handout so you don't have to draw all those figures. So let's get started. So gears, pulleys, and sprockets, the reason they put these all together is because basically they do the same function, even though they look slightly different. They change the speed of rotation, so it goes from slow to faster, change the direction, clockwise to counterclockwise, and they can increase the torque. And this is the first time we've heard the word torque. Basically, we talk about force when we're talking about a push or a pull, and torque is just when we have a turn. It's like a force when we're doing a turn. So gears, they look like this. And a gear train is when I just have more than one. They cause rotary motion, that's the circular motion. And they have the teeth on them. The little bumps, those are the teeth. Mating gears always turn in opposite directions. If you notice, this one is going clockwise, this one's going counterclockwise. Here, this one's going clockwise, counterclockwise. An idler gear is this one in the middle, and basically it just means that the two blue ones here can turn in the same direction. Notice that even though these two whole gears are not the same size, the teeth on the gears are the same size so that they can mesh together. RPMs, revolutions per minute. We saw that already with wheels. Larger gears move slower than smaller gears. But if I put both of these on the same axle, where these are glued together on the same axle, these two will turn at the same rate. Okay. I think you have this picture here at the top, and we're just going to talk through the formulas. And I'm going to talk through these variables. N stands for the number of teeth, D is diameter. This is an omega symbol. It's like a W, but it's an omega, and it's a lowercase omega, and it means angular velocity. So how fast something is spinning. And then torque we talked about, it's like a force, but we're talking about a turning force, and that's a tau. A Greek capital letter tau represents torque. These formulas and these variables are found on your formula sheet at the back of your book. So here, if I have this is my N, this is like my effort. If we think about it the same way as we did with simple machines, we have effort and load. Here we talk about where my N is, that's like your effort, and your out is like your load. So on my inside, this one has 6 teeth, and I'm reading right here. It has a diameter of 2 inches. It's turning at 40 RPM, that's the omega, the angular velocity, and it would have a torque of 40 foot-pounds. This is my out, and you can see if you count, there's 12 teeth. It's a 4-inch diameter, 20 RPM, and 80 torque out. Now let me talk about this foot-pounds right here. This is not feet per pound, this is feet times pounds. You just have to trust me on this. It's feet times pounds is the units on this. We'll talk about this later on when we get to some other things, but for now, just realize it's feet times pounds, not feet per pound. So here's our equations to know. Just like we had MA for mechanical advantage with our simple machines, now we have gear ratios. It's very similar. GR is how we write it. And here's the formula, which looks super long. This is in your formula chart. This looks super long, but basically it's just proportions. So for this set here, we just line the proportions up. If I want to find out the gear ratio, for these gears here we just saw on the previous page, I could do it by doing N out over N in, which would be 12 over 6. Or I could use the diameters, 4 over 2. Or I could use the omegas. Notice on the omegas they get flipped, and the N is on top, so that's 40 over 20. Or the taus, which is 80 over 40. Now notice what they've done on these units. When I have the same units on top and bottom, they cancel out. So if all my units cancel, what kind of units do we have for gear ratio? That's right, it has no units, just like mechanical advantage. So here, no matter which one of these I use, I would get a gear ratio of 2. Okay, so you have this problem, and we're going to actually calculate the gear ratio between A and B. You do have to look at which ones they're talking about, and when they say the gear ratio between A and B, they always mean this is the in and that's the out. So let's do it with the number of teeth, because they didn't tell us anything else here other than how many teeth it is. So the out is going to be 12 and the in is going to be 20, and they reduced it to 0.6. Now let's do it from B to C. Again, this is in and out, so that would be 5 over 12 or 0.42. And finally, from C to D, that would be in, out. So it's 20 over 5, or 4. So what would be the total gear ratio of this whole thing? Remember, it says idler gears don't affect the gear ratio, so these middle ones actually don't have anything to do with the gear ratio. I could take all 3 of my gear ratios I got. This was the one from here to here, this was the one from here to here, and this is the one from there to there, and I can multiply them out and find that it's a gear ratio of 1. Or if I directly go A to D, I'd see that my out over my in is 20 over 20, and it's still 1. So if you're finding the gear ratio of a whole train, you only need to know the first one and the last one. The middle ones don't make any difference. What if the last one was 40 teeth? Well, we just use this part right here, and we would find that it's going to be 2, or I could go through the whole process again to find out it's 2. Easier just to use the first and last one. Okay, compound machines, we're going to skip this. Okay, here's our next one. Now, first of all, you need to look at what this is doing. This is a gear, and this arm is attached on there, and this is another gear, and this is attached on there. So these arms move when the gear moves. If I push this effort load here, it's going to turn this one this way, and it's going to turn this one this way and turn this arm as well. And take a minute, glue this picture into your notebook. It's one of the pictures I gave you. And take a second to write down what we know about each one. What is the N? What is the diameter of each one that we're going to use? So here we have several mechanisms. We have wheel axle, that's a simple machine. Then we have the gears in the middle, and then we have a wheel axle over here. Even though it doesn't look like a wheel, this works like a wheel because here's the axle and here's the diameter of this part right here. And we're going to have to calculate each independent piece. So first we're going to look at this wheel right here. So we're using mechanical advantage from when we did simple machines. We have a diameter of 4 over a diameter of 1.5 from this part, giving us a mechanical advantage of this. Write that part down and then move on. Now we're going to do the gear train part in the middle. Gear train, teeth out over teeth in, so that's going to be 24 over 60, 0.4. Write this part down before you move on to the last part. Now we have the mechanical advantage of our last wheel and axle. Again, we're doing with diameters. Diameter effort is coming from here at 0.6. Diameter resistance is at the 4 over here. Put those in and calculate. Write that down. So I now have 3 parts: mechanical advantage, gear ratio, mechanical advantage that you just wrote down. To find the total mechanical advantage of the whole thing, we'd multiply the 2 mechanical advantages together and get 0.4. And to get the total gear resistance, well, there was only 1 in the middle, it'd be 0.4. Okay, we're going to pause here and then we'll pick this up in part 2.